We were talking last time about the Hall effect. Which we said was this polarization that occurs when you're running a current in the presence of a magnetic field. And so you get a polarization that occurs that's transverse or perpendicular to the direction of the conventional current. Okay, so that's called the Hall effect. And we said that this was one way to distinguish whether the charge carriers or the mobile charges inside a material were in fact positive or negative. And of course, we've been dealing with mostly negative charge carriers in metals, but there are, we talked about these not superconductors, but semiconductors, which occasionally can have situations where the charge carriers are positive, these sort of holes in the electron structure which behave like they're positive charges. So this is a possibility. And we left off last time looking at this problem, which I've redrawn. And there's a couple of different questions we can ask here. Are the mobile charges electrons or holes? We did that last time, but let's just real quick run through this again. We were saying that in order to think about this question, if we want to write just some guidelines or tips down for dealing with the Hall effect, if I can spell it, first thing you want to do is draw the direction of the parallel electric field. What do I mean by E parallel? What was that again? That's which electric field? Driving the current. Okay, parallel to, meaning parallel to the flow of electrons, parallel to the current. Okay, so we have, in this problem, we have let's draw an orange here, battery or a power supply. Here's the positive terminal, here's the negative terminal. So in the bar of material here, E parallel should be pointing what direction? Everybody point. That way, right? That way. That's E parallel. Which means we could either have positive charges moving which way? That way? Okay, so we could have plus charges moving that way, or negative charges moving the opposite direction. Okay. So once you've narrowed it down to those two possibilities, you can then try both cases, right? Plus charges in the direction of E parallel, or minus in direction or in opposite direction of E parallel. And what we're looking for is which case gives us the correct voltmeter reading. If we already know the voltmeter reading on this perpendicular or Hall effect voltage, then we can try either and see which one gives us the correct effect. And for that we need to figure out the direction of the magnetic force on these mobile charges. And so the magnetic field, here's the bar magnet, here's the south pole, magnetic field's pointing which way? Kind of towards it, all right? That's B. So you can think of it in this perspective, it's kind of into the page here, right? B is pointing into the page. So we try a positive charge moving this way. The force is going to be what? V cross B is in, force is down. Okay, so we get a polarization where on the bottom I'm going to draw positive charges. On the top I draw negative. Does that agree with the voltmeter reading? Does that agree with the voltmeter reading? The voltmeter reading is positive, and the positive terminal connected to the higher potential should give us a positive reading. Is the plus terminal in fact connected to the higher potential? Yeah, okay. So this works, okay? And if it had been negatives, we'd have gotten V cross B is up, but we had a negative charge, so we have to flip the direction. We've gotten the opposite polarization. That would not have agreed with the voltmeter reading. Okay, so just a review of last time. So we know it's got to be positive charges. So question number 1 is done. Part 2 is, what is the magnetic dipole moment of the bar magnet? Well, that sounds like a question that has absolutely nothing to do with anything going on in this problem. But you want to if you start from fundamental principles, you can actually get there. And one kind of nice thing or interesting thing about Hall effect problems is that they kind of bring together just about everything we've done in the course so far. Okay, we're talking about polarization, we're talking about electric fields, magnetic fields, electric forces and magnetic forces, circuit applications, currents, and so forth. So let's just see where we can start to try to make sense of a problem like this. And in the steady state, so I guess one other tip or one other suggestion you can say when you're dealing with a problem like this is focus on motion of one mobile charge in the steady state. And analyze its motion, starting from fundamental principles there, and see where it leads you. So here is our positive charge. Here's our single positive charge. Let me draw it again here. Give ourselves some room. We have a positive charge moving in this direction, so I'll draw its velocity v. And again, that's E parallels that way. And so we indicated the polarization. So what's the direction of the perpendicular electric field? Pointing up, right? From the positives on the bottom to the negatives on the top. So that's E perpendicular. So in the steady state, there's going to be forces, magnetic and electric forces acting on the mobile charge. We said the magnetic force was what direction? The V cross B force was down, okay. Let me draw that in. That's magnetic force. But now we have this E perpendicular, and that force is going to be up. It's going to be up. What do I know about those two forces in the steady state on that single mobile charge? The net force is 0 because in the steady state, these charges should be moving through at a constant velocity or a roughly constant velocity, right? On average velocity constant. So there shouldn't be any more deflection up or down. The polarization is already done and settled down. So that's where we start, right? The fundamental principle here is essentially Newton's second law, or the momentum principle. Rate of change of momentum is equal to the net force. In the y direction and in the perpendicular direction, there is no change in the momentum anymore. There's no acceleration up or down. So the net force is equal to 0. That means the electric force, the perpendicular electric force, be careful between the two electric fields here, is equal to the magnetic force. Okay. Okay, well, we're trying to find the magnetic dipole moment of this bar magnet, so hopefully the magnetic field is going to show up someplace. Well, what's the magnetic force? What's the formula for that? QV cross B, right? QV cross B, we're looking at the magnitude. QV cross B. So we have the magnitude of V times the magnitude of B times the sine of what angle? 90 degrees. Sine of 90 is 1. So we end up with Q times V times B. So we're getting closer because we now have a B in this equation, which should have some relationship to the magnetic dipole moment. What's the electric force? QE. Which E? Perpendicular, not the parallel. It's the perpendicular one, right? E perpendicular. So the Q's cancel out. And so we have the magnetic field showing up in here, and we have E is equal to E perpendicular is equal to V times B. Well, okay. We don't know B, but that is essentially has the information we're going to need to find it, because that is how we're going to get to the magnetic dipole moment. We don't know the speed, and we don't know E perpendicular. Well, has that helped? Can we figure out E perpendicular? Can we relate it to something in the problem, something that's given? The delta V, right? We're given the perpendicular delta V. So delta V perpendicular, how does it relate to E perpendicular? Just the magnitude of it. It's going to be E dot L. Which L, right? What distance do we need to use here? The height, that's right. So we're going to have E times H, where H is this 2.5 centimeters, okay? So let's calculate the electric field. Let's just get a number. So if you have a calculator, break it out. We have 1.2 times 10 to the minus 5 volts divided by a height of 2.5 centimeters, so that's 2.5 times 10 to the minus 2 meters. What do we get for E perpendicular? What is it again? 4.8 times 10 to the negative 4. Is that right? Yeah. Volts per meter. Okay. All right, so that's E perpendicular. Getting closer. So we've got this part. What about V? What about the velocity? How are we going to figure out the velocity of one of those mobile charges? Okay, the current. The current's going to play some role, right? Because the current's related to the velocity. How? Here, I equals N. Yeah, NAV. And then, well, we don't know the current yet, right? So that maybe that's a dead end. But what do we do know? Okay, we know the area. We know something else. We know the voltage. Okay, getting closer, right? We know the voltage across either end of the bar. That could tell us what? We know this voltage. We know the length. What could we figure out? Which electric field? Parallel electric field, right? So we could figure out the E parallel same way by saying it's delta V, really the EMF in this case, just divided by what length? L, right? 12 centimeters. Well, if we knew that, we need to know something else. There is actually something else we need to know, which I forgot to write down, which is, what if we knew the mobility? So the mobility, let's say, of this material happens to be 1 times 10 to the minus 7. Thank you. 1 times 10 to the minus 7 meters per second over volts per meter. A little hard to solve this without that. While we're doing it, let's say the number density of electrons is 3 times 10 to the 25th electrons per cubic meter. Okay. If we know the mobility, how do we relate it to the drift speed? V equals UE. V equals UE. Okay. So now we can figure out the drift speed, right? We can say that V is equal to the mobility, which is 1 times 10 to the minus 7. The electric field is going to be the EMF, 240 volts, divided by the length of 12 centimeters, so that's 0.12 meters. So what do we get for the drift speed? Calculate it. 2 times 10 to the negative 4 meters per second. Okay. Finally, we've got E perpendicular. We've got the drift speed. We can solve for the magnetic field. Let's at least do that. B is going to be E perpendicular divided by the drift speed, which is 4.8 times 10 to the minus 4 volts per meter over 2 times 10 to the minus 4 meters per second. And what's that give us? 10 to the minus 4 cancels out. 2.4, right? 2.4 Tesla, is that right? Which is a pretty large magnetic field. Okay, so we're going to get a very large magnetic dipole moment. Everybody okay here? If we do the calculations correctly? Everything look okay? So finally, how would you figure out the magnetic dipole moment of the bar magnet? How do you relate the magnetic field to the dipole moment? Anybody remember It's a formula due to magnetic, or the magnetic field due to a magnetic dipole is what? Depends on what's the distance dependence. R squared, R cubed, right? It's this 1 over R cubed dependence. Remember this? It was B is equal to mu naught over 4 pi 2 mu over the distance cubed. Okay. So mu here is the magnetic dipole moment, essentially the strength of the bar magnet. We could solve for that at this point. And it looks like we're probably going to get a pretty high number here, but so we have B magnetic field times the distance cubed divided by 2 divided by mu naught over 4 pi. So we have 2.4 Teslas times 0.2 meters cubed divided by 2 divided by 1 times 10 to the minus 7, which gives us what? Plug it in. 96,000? Okay, it's a pretty large magnetic dipole moment, 9.6 times 10 to the fourth, and the units are amp meters squared. So I didn't actually get this number earlier, so I'm not sure if we did something wrong here, but I don't see anything coming out. But it's a large dipole moment, so it's not going to be something, probably a bar magnet is not something that's going to be able to generate a magnetic field that high. But if you had very large coils of wire with very high currents running in them, you could actually generate a pretty high magnetic field, and you have a very large dipole moment corresponding to that generated field. So it's just an example of how we're kind of bringing a lot of stuff together, right? We've got the issues with dealing with circuits, dealing with the relationship between drift speed and electric fields and mobility, dealing with potential differences, dealing with magnetic forces, dealing with magnetic fields due to dipoles, kind of all coming together into one problem. And you're going to be expected to do things like this on the homework and on the test, okay? But so you want to figure out where can you start? And starting by looking at the motion, relating the forces on a single moving charge, and then just going from there, seeing what's unknown and seeing where you can figure out other things from. Remember, the loop rule and the node rule still apply, so we can use our circuit analysis tool techniques and so forth to deal with this. Questions on any of this? The last question was just on the current. The conventional current, well, the conventional current we know is going to be flowing in what direction? Capital I through the bar is flowing what direction? That way, right? So capital I flowing into the ammeter, flowing into the positive terminal of the ammeter and flowing out of the negative terminal of the ammeter. Let's see, the potential, let's see, which is the higher potential? The electric field is pointing from the higher to lower potential. So this is the higher potential. So we should get a positive value for the current here. And then the conventional current we could figure out now by saying Q N A U times E. Which E? Parallel E, okay? At this point we would know everything. We've got everything we need to know. What area do we use? What's the cross-sectional area that we would need to use to calculate this current? Is it L times H? D times H? L times D? The current's flowing which way? It's flowing this way, right? So it's flowing through, if you imagine sort of cutting a surface and looking at whether charges pass through that surface or not, which surface is the charges going through? The D times H area, right? So the cross-sectional area, this is the cross-sectional area. So that's another pitfall that you may run into. This is the cross-sectional area. They're passing through this surface. Area is going to be D times H. We could plug it in and figure it out at this point because we have all the other given information. Okay? Questions? So this, again, we're bringing everything together. you'll be solving problems that may be variations on this, where you're asked to find the sign of the charge carriers. You may be asked to find some unknown. Might be the mobility. We actually have a way now. If we had been given the magnetic field instead of being asked to solve for it, we could have, and given the current, for example, we could have used this to solve for the unknown mobility. Okay, and that's actually one method, I believe, where mobilities are measured. We can actually use the Hall effect to measure mobility. And the Hall effect has other various technical applications as well. Other questions? Let's try a question, since we've been doing this for quite a while. Oops. So another application of the Hall effect here, we have a long bar, and I'm just showing sort of a cross-section of this bar. So you can imagine this bar connected to a circuit somewhere, and it stretches out along the x-axis. And I measured the voltmeter. Voltmeter 1 measures the potential difference across the length of the bar, and voltmeter 2 is measuring the potential difference perpendicular to the bar, okay, perpendicular to the length of the bar. And the magnetic field is pointing outward. So there's some applied magnetic field due to coils not shown pointing outward. Voltmeter 1 has a reading that is positive, and voltmeter 2's reading is also positive. What's the sign of the mobile charge carriers? Again, think about the steps. See if you can figure out the direction of the electric fields. Try both cases. See which one gives you the correct voltmeter readings. Okay. Bare majority for answer number 2. Okay, so how would you figure this out? The first thing, again, you have to figure out is the direction of E parallel. We're told something about the voltmeter reading here, that it is positive. All right. The rule, what's the rule again for a voltmeter? If the positive terminal is connected to the higher potential, it reads positive. Okay. This is reading positive. So which end is at the higher potential? The right. Okay, so we have the high potential over here, low potential over here. Once you know that, this meter is going to give us the direction of which electric field, parallel or perpendicular? Parallel. So once you know this, what's the direction of E parallel? Points that way. Okay. That's E parallel. So we've got step 1 down. Now let's try step 2. Let's think about positives moving in the direction of E parallel or negatives moving in the opposite direction. So let's try positives moving this way. Here's a positive moving in the direction of E parallel. The magnetic field is pointing out, so the magnetic force would be what? Be up, right? Be up. So on the top, I would get a buildup of positive charge. On the bottom, I would get a buildup of negative charge. But does that agree with voltmeter reading 2? No, why not? The electric field in this case would be pointing down, which would mean that this is the higher potential, but this end is connected to the negative terminal, right? Again, the rule is if this is, we know this is reading positive. And so if it's connected to, it's got to be the case that this is connected to the higher potential and this is connected to the lower potential. But if we do this case, it's not. So that's not going to work. That's not going to work. Okay, so that's ruled out. We must not have this situation. The only other possibility, and let's just go through it to check it, negatives moving that way, right? Negatives moving in that direction would have a force in what direction? V cross B is down, but what do? Flip it because it's a negative. I get negatives on the top, positives on the bottom. Does that work? Yeah, that works. Okay. You see what I have to go through here? I mean, these are the steps that this is one of these things where it's hard to just take a guess. Okay, it's hard to just look at it and see what the situation is. You really have to kind of go through the procedure and try it out and just work it out, you know, step by step and see which one gives you the correct case. Okay. Questions? All right. Well, you will have some practice on this for the homework upcoming, and in an upcoming lab too, you'll have a problem, whiteboard problem similar to one of these as well.